Welcome. Today we're going to explore one of the most important functions in trigonometry, the tangent function. Whether you're studying for a test or just curious about mathematics, this video will give you a solid understanding of what tangent is and how it works. The tangent function comes from right triangles. In any right triangle, we can identify three sides: the side opposite to our angle of interest, the side adjacent to our angle, and the hypotenuse, which is always the longest side opposite the right angle. The tangent of an angle theta is defined as the ratio of the opposite side to the adjacent side. This can also be expressed as sine theta divided by cosine theta. This simple ratio gives us a powerful tool for solving problems involving angles and distances. Throughout this video, we'll explore how to calculate tangent values, see how architects use tangent to design building overhangs, and discover how navigators use this function to find distances and directions. By the end, you'll have a complete understanding of this essential trigonometric function. Ready to master the tangent function? In the next section, we'll start with the formal definition and build your understanding step by step. The tangent function can be defined in two equivalent ways. Understanding both definitions will give you a complete picture of what tangent really means mathematically. The first definition is algebraic. The tangent of an angle theta is defined as the ratio of the sine of that angle to the cosine of that angle. This tells us that tangent is fundamentally connected to the sine and cosine functions. Wherever cosine is 0, tangent will be undefined, which is an important property we'll explore later. Now let's see what this means geometrically. In a right triangle, we can identify three sides relative to our angle theta. We have the hypotenuse, which is the longest side opposite the right angle, the side opposite to our angle theta, and the side adjacent to our angle theta. In this right triangle, the tangent of theta is defined as the length of the opposite side divided by the length of the adjacent side. Notice how both definitions give us the same result. The algebraic definition using sine and cosine is equivalent to the geometric definition using opposite and adjacent sides. There's one more important relationship to understand. The tangent function is the reciprocal of the cotangent function. We can also express cotangent in terms of sine and cosine. Since cotangent is the reciprocal of tangent, it equals cosine divided by sine. In the right triangle, cotangent represents the adjacent side divided by the opposite side, exactly the reverse of tangent. These definitions form the foundation for understanding the tangent function. Whether you think of it algebraically as sine over cosine or geometrically as opposite over adjacent, you're describing the same mathematical relationship. Now we'll explore how the tangent function appears on the unit circle. The unit circle provides us with a powerful geometric way to understand what tangent really means. For any angle theta, we can find a point on the unit circle. This point has coordinates that are directly related to the cosine and sine of the angle. The x-coordinate of this point equals cosine of theta, and the y-coordinate equals sine of theta. These are the fundamental relationships we use to define tangent. The tangent of theta is defined as y divided by x, which is the same as sine theta divided by cosine theta. This ratio has a special geometric meaning. Notice that this ratio represents the slope of the line from the origin to our point on the circle. The tangent function literally gives us the slope of this radius line. Let's examine specific examples. First, when theta equals 30 degrees or pi over 6 radians, watch how the coordinates and tangent value change. Now let's move to 45 degrees or pi over 4 radians. At this special angle, the x and y coordinates are equal, making the tangent equal to 1. Now comes the most important case. Watch what happens as we approach 90 degrees. The x-coordinate gets closer and closer to 0, while y approaches 1. When the x-coordinate equals 0, we're dividing by 0, which makes the tangent function undefined. This creates what we call a vertical asymptote. Let's see how the tangent changes as we move around the circle. Notice how the tangent value grows very large as we approach 90 degrees, becomes undefined at exactly 90 degrees, then jumps to large negative values just past 90 degrees. The unit circle gives us a clear geometric understanding of tangent. It's the ratio of y to x coordinates. It represents the slope of the radius line, and it becomes undefined whenever the x-coordinate is 0. Now we'll explore two crucial properties of the tangent function: its vertical asymptotes and its symmetry. These characteristics help us understand the function's behavior and make graphing much easier. Vertical asymptotes are invisible vertical lines where the tangent function shoots up to positive infinity or down to negative infinity. These occur at specific, predictable locations. The formula for finding vertical asymptotes is x equals pi over 2 plus k pi, where k is any integer. This means asymptotes occur at pi over 2, negative pi over 2, 3 pi over 2, negative 3 pi over 2, and so on. Let's visualize this on a coordinate system. I'll show you exactly where these asymptotes appear and how the tangent function behaves around them. Here are the vertical asymptotes shown as red dashed lines. Notice they occur at negative 3 pi over 2, negative pi over 2, pi over 2, and 3 pi over 2. The pattern continues infinitely in both directions. Now I'll draw the tangent function itself. Watch how the curve approaches the asymptotes, but never actually touches them. The function shoots up to positive infinity on one side and down to negative infinity on the other side of each asymptote. The tangent function is what we call an odd function, which means it has rotational symmetry about the origin. This creates a very specific mathematical relationship. The mathematical way to express this symmetry is tangent of negative theta equals negative tangent of theta. This means if you know the tangent of any positive angle, you automatically know the tangent of the corresponding negative angle. Let's work through our first example. We need to find the first three positive asymptotes of the tangent function. We'll use our formula step by step. We start with our asymptote formula. For positive asymptotes, we need positive values of k. Let's use k equals 0, 1, and 2. For k equals 0, x equals pi over 2 plus 0 times pi, which equals pi over 2. For k equals 1, x equals pi over 2 plus 1 times pi, which equals 3 pi over 2. For k equals 2, x equals pi over 2 plus 2 times pi, which equals 5 pi over 2. Therefore, the first three positive asymptotes are pi over 2, 3 pi over 2, and 5 pi over 2. For our second example, we'll use the odd function property. We know that tangent of pi over 4 equals 1. We need to find tangent of negative pi over 4. We're given that tangent of pi over 4 equals 1, and we need to find tangent of negative pi over 4. We apply the odd function property. Tangent of negative theta equals negative tangent of theta. Substituting our angle, tangent of negative pi over 4 equals negative tangent of pi over 4. Since tangent of pi over 4 equals 1, we get tangent of negative pi over 4 equals negative 1. For our final example, we need to count how many vertical asymptotes the tangent function has in the interval from negative 2 pi to positive 2 pi. This requires systematic thinking. Our approach is to find all values where x equals pi over 2 plus k pi that fall within our given interval. We need negative 2 pi to be less than or equal to pi over 2 plus k pi, which must be less than or equal to positive 2 pi. Subtracting pi over 2 from all parts, negative 2 pi minus pi over 2 is less than or equal to k pi, which is less than or equal to 2 pi minus pi over 2. This simplifies to negative 5 pi over 2 is less than or equal to k pi, which is less than or equal to 3 pi over 2. Dividing by pi, negative 5 over 2 is less than or equal to k, which is less than or equal to 3 over 2. Since k must be an integer, the possible values are negative 2, negative 1, 0, and 1. Therefore, there are 4 vertical asymptotes in the given interval. To summarize this section, vertical asymptotes occur at x equals pi over 2 plus k pi. The tangent function is odd, meaning tan of negative theta equals negative tan of theta. These properties are essential for understanding and graphing the tangent function. The tangent function isn't just an abstract mathematical concept. It has powerful real-world applications that directly impact our daily lives. In architecture, the tangent function plays a crucial role in designing buildings that are both energy efficient and comfortable. One of the most important challenges architects face is designing roof overhangs. These overhangs must block the harsh summer sun to reduce cooling costs while still allowing beneficial winter sunlight to enter the building. They also need to protect the structure from rain and weather. To solve this problem, we can model it geometrically. Here we have a cross-section of a house with a roof overhang. The overhang extends horizontally from the wall, and we need to determine its optimal length. Now we add the sun at a high angle, typical of summer in Florida. The sun's rays create a shadow, and we can see how the overhang blocks sunlight from reaching the wall below. The key insight is that this creates a right triangle. The overhang length is the adjacent side, the shadow length is the opposite side, and the sun ray is the hypotenuse. The angle theta is the sun's elevation angle. The mathematical relationship is based on the tangent function. Tangent of the sun angle equals the opposite side over the adjacent side, which is the shadow length divided by the overhang length. We can rearrange this formula to solve for the overhang length. The overhang length equals the desired shadow length divided by the tangent of the sun angle. Now let's work through the actual Florida example. In Florida, the summer sun reaches a high angle of approximately 78 degrees. Architects want to create an 8-foot shadow to protect the wall and windows. We need to find the required overhang length. Step 1. We start with our rearranged formula. The overhang length equals the shadow length divided by the tangent of the angle. Step 2. We substitute our known values. The shadow length is 8 feet and the angle is 78 degrees. Step 3. We calculate the tangent of 78 degrees. Using a calculator, we find that tangent of 78 degrees is approximately 4.705. Step 4. Now we divide 8 by 4.705 to get approximately 1.7 feet. This is very close to the 2.2 feet mentioned in the research, with the difference likely due to additional design factors. Therefore, the required overhang length is approximately 1.7 feet. This calculation shows how the tangent function directly determines the architectural design needed for optimal sun protection. The practical impact of using the tangent function in architectural design is significant. Proper overhang design can reduce cooling costs by up to 30%, improve indoor comfort, protect building materials from weather damage, and increase property value. This example demonstrates how the tangent function transforms abstract mathematics into practical, cost-saving architectural solutions. What might seem like a simple trigonometric calculation actually has profound real-world implications for energy efficiency and building design. The tangent function extends far beyond theoretical mathematics into practical applications that shape our modern world. Today, we'll explore 3 critical areas where tangent calculations are essential: maritime navigation, physics modeling, and computer graphics. In maritime navigation, sailors use sextants to measure vertical angles to landmarks like lighthouses. The tangent function converts these angle measurements into precise distance calculations, essential for safe navigation. In physics, the tangent function models projectile motion and oscillations. It relates velocity components, helping us predict trajectories and analyze periodic phenomena like pendulum swings. Computer graphics rely heavily on tangent calculations for object rotations and transformations. Every time you rotate an image or animate a character, tangent functions compute the new coordinate positions. Our first example demonstrates navigation calculations. A sailor uses a sextant to measure a 15-degree angle to a lighthouse that is 120 feet tall. We need to find the horizontal distance to shore. We set up our diagram with the ship, lighthouse, and measured angle. The lighthouse height is our opposite side, and the unknown distance is our adjacent side. Step 1. We write the tangent ratio. Tangent of 15 degrees equals the opposite side, 120 feet, divided by the adjacent side, d. Step 2. We multiply both sides by d to isolate the tangent term. This gives us d times tangent of 15 degrees equals 120. Step 3. We divide both sides by tangent of 15 degrees to solve for d. Distance equals 120 divided by tangent of 15 degrees. Step 4. We calculate the numerical value. Tangent of 15 degrees is approximately 0.2679. So d equals 120 divided by 0.2679, which gives us approximately 448 feet. Example 2 involves projectile motion. A projectile is launched with an initial velocity of 50 meters per second at angle theta. If the horizontal velocity component is 40 meters per second, we need to find the launch angle theta. We draw a velocity vector diagram. The total velocity is 50 meters per second. The horizontal component is 40 meters per second, and we need to find the angle theta. Step 1. The horizontal velocity component equals the initial velocity times cosine of theta. We know this equals 40 meters per second. Step 2. We solve for cosine of theta by dividing 40 by 50, which gives us 0.8. Step 3. The vertical velocity component equals 50 times sine of theta. We can find this using the Pythagorean identity. Step 4. Using the identity sine squared plus cosine squared equals 1, we find sine of theta equals square root of 1 minus 0.64, which equals 0.6. Step 5. Now we can find tangent of theta. Tangent equals sine divided by cosine, which is 0.6 divided by 0.8, giving us 0.75. Step 6. Finally, we take the inverse tangent of 0.75 to find theta equals approximately 36.87 degrees. Our final example demonstrates computer graphics transformations. We need to rotate point P with coordinates 4, 3 by 30 degrees counterclockwise around the origin and find the new coordinates. We set up a coordinate system and mark the original point P at coordinates 4, 3. We draw a vector from the origin to this point. The rotation transformation formulas are x prime equals x cosine theta minus y sine theta, and y prime equals x sine theta plus y cosine theta. Step 1, we substitute our values. X equals 4, y equals 3, and theta equals 30 degrees. Step 2, we recall that cosine of 30 degrees equals square root of 3 over 2, approximately 0.866, and sine of 30 degrees equals 1/2 or 0.5. Step 3, we calculate the new coordinates. X prime equals 4 times 0.866 minus 3 times 0.5, which gives us 1.964. Y prime equals 4 times 0.5 plus 3 times 0.866, which gives us 4.598. Step 4, we plot the new point P prime at coordinates 1.96, 4.60. Notice how the point has rotated 30 degrees counterclockwise around the origin, maintaining the same distance from the center. These 3 examples demonstrate the tangent function's versatility across navigation, physics, and computer graphics. From calculating distances at sea to modeling projectile trajectories and rotating digital objects, tangent provides the mathematical foundation for countless real-world applications. We've covered a lot of ground in our exploration of the tangent function. Now it's time to bring everything together and summarize the key concepts that make this trigonometric function so powerful and versatile. First and foremost, the tangent function is defined as the ratio of sine to cosine. This fundamental relationship gives us tan theta equals sine theta divided by cosine theta. In the context of a right triangle, this translates to the ratio of the opposite side to the adjacent side. The tangent function has several crucial properties that distinguish it from other trigonometric functions. It has a period of pi, meaning it repeats every pi units. Its domain excludes points where cosine equals 0, creating vertical asymptotes. The range spans all real numbers, and it's an odd function, which means it has rotational symmetry about the origin. Let's visualize these concepts on the unit circle to reinforce our understanding. On the unit circle, the graph of the tangent function shows its periodic nature with a period of pi and the vertical asymptotes where the function is undefined. Notice how the function increases from negative infinity to positive infinity within each period. Now let's recap the real-world applications that make the tangent function so valuable in practical problem solving. The tangent function finds applications across numerous fields. In architecture, it helps calculate optimal roof overhangs and building angles. In navigation, it's essential for distance calculations and bearing measurements. In computer graphics, it enables 3-dimensional rotations and perspective projections. Remember, at its core, the tangent function represents this fundamental relationship between sine and cosine, or in geometric terms, the ratio of opposite to adjacent sides in a right triangle. Understanding the tangent function opens doors to solving a wide array of mathematical and real-world problems. You now have a solid foundation in the tangent function. You understand its definition, properties, graphical behavior, and practical applications. This knowledge will serve you well in advanced mathematics, physics, engineering, and many other fields. Thanks for joining me on this journey through the tangent function. If you found this helpful, please like this video, leave a comment with your questions or topics you'd like to see covered, and subscribe for more mathematics tutorials. Keep practicing, and remember that mastering mathematics is a journey of continuous learning and discovery.